is not covered in the lecture outline. So this is totally new material. I apologize for this. The question says, draw a picture of the following orbitals, A, 1s, 2s, and 3s on the same set of axes. Let's tackle that one first. And although we've talked somewhat about this and we've done some calculations with this, so 1s, 2s, and 3s. So let's do A here. If we draw them on the same set of axes, and the S sublevels in which there is only one orbital are all spheres. And so when we draw them, we draw circles. And where previously we would call this n equals 1, we are now calling this 1s. And 2s is bigger than that. And I don't know if I'm going to actually draw them to scale because the sizes are there's not a linear difference between them in the sizes. But we do know that 2s is larger than 1s. And 3s is larger than 2s. Okay. And 4s and 5s and 6s just get increasingly larger. And these are really spheres, but we're drawing them as circles. Okay? And that's actually the answer for letter A. For letter B, we will now draw the 2s and 2px on the same set of axes. The 2s, I'm going to try and draw exactly the same. So I'm going to try and draw it just like I did over here. It's going to be a sphere. It's going to be about this big. And again, I'm drawing the sphere as a circle. And that's 2s. Now, again, this is something I don't think I covered. I don't think I covered the 2p shapes of the orbitals, but a 2p orbital looks like this. And I'm going to draw it in red. And a 2p orbital has two lobes. Two lobes or two parts. I'm going to zoom in here and see if we can get a slightly better focus on this. Two lobes or two parts. And this is one orbital. And I'm going to call this the x-axis here. And because of that, this is going to be 2px. And the reason I wanted you to draw this, even though I didn't cover it in the lecture, this is an important point, the lecture outlines that is that you can see that the 2s and the 2p orbitals both end at approximately the same distance from the nucleus. That's an important point, so I'm going to write it down. So the 2s and 2p orbitals both end at approximately the same distance from the nucleus. Both end at approximately, and there's my squiggly equal sign, the same distance from the nucleus. So, and that's what we're trying to do here. And sort of the way I think about this is that when you have a 1s sublevel and a 1s orbital, there's only one way to put electrons in there. So there's only one orbital in all of the 1s and the n equals 1 sublevel. And then for n equals 2, the sphere is bigger. So the first two electrons go into what's called the 2s orbital and the 2s sublevel. But there's still enough room that you can fit more electrons in there. And they start going into the 2p sublevel. And in fact, for 2p, there are 3 orbitals. and one of them is shown here. Okay. Any questions about that? One question that could come up is, okay, if this is one orbital, and it's true that I've drawn it, that it is not touching the nucleus is at the center portion right here, then how does an electron get from part of the orbital to the other part of the orbital? And I will say a couple things. One is, remember, all of these shapes that we are drawing for these orbitals are the volume of space in which there is a 90% probability of finding the electron. And half of that probability would be on this left side, half of that probability would be on the right side. And it is true that there is no probability of the electron, or a very nearly infinitely small probability of it being in here. And it can jump from one portion to the other. And that jumping is called electron tunneling. And it comes from the fact that electrons exist as probabilities. And there's a very small probability that it will be right here. And then it effectively jumps over from one place to another. Well, and we know that from last time, electrons are interesting creatures. They exist as probabilities. And again, all of these shapes, and let me just make sure I cover this. This should have been covered in the lecture outlines. The definition of an orbital. An orbital is the volume of space in which there is a 90% probability of finding the electron. A 90% probability of finding the electron. Okay, these are 90% probabilities, and the probability outside of each of these orbitals decreases exponentially as you get outside of these spaces. Anyway, I know it's a little frustrating for me because I'm showing you the results of quantum mechanics without actually doing any of the math. The math does require integration in 3 dimensions, and to solve this kind of math, you need to be through 3rd semester calculus, which I once did but have long forgotten, although it's fun to think about sometimes. But sort of that's the frustrating thing about this course. One of them is that we are dealing with the results without really getting into the math or being able to. Anyway, so in summary, a p orbital has 2 lobes. It's often called a dumbbell, and it's often represented by 2 balloons, because there can be balloon shapes as well. Now for C, it says, draw the 2px, the 2py, and the 2pz orbitals on the same set of axes. I'll do that down here. And just to remind you, the 2p sublevel has 3 orbitals, and each orbital holds 2 electrons, so for a total of 6 electrons. And when we do our electron configurations, we'll actually write 2p6. That'll be the 2p sublevel with 3 orbitals, each orbital holding 2 electrons for a max of 6 electrons. Anyway, so now let me actually answer this question. So 2px, 2py, and 2pz are going to be shapes just like this along each of their respective axes. So I'll draw them actually in, I think, 3 different colors. Do I have... No, I only have 3 colors. I thought I might even have 4 colors here, but let's see. So the nucleus always at the origin I just drew for you 2px. Let me draw for you again. When you draw them, do not touch the nucleus. It gets very close, but it does not touch the nucleus. And then there's for sort of spherical. And they're supposed to be the same size. Mine's a little smaller on this side, but hopefully you get the idea. And again, that is 2px because I've defined this as the x-axis. The atom can't tell its x from its y from its z-axes, but we will assign a configuration. Now let's call this the y-axis. And for the y-axis, these two shapes will be along the y-axis. And they should be the same shapes. My attempts at drawing them may not be. So this is 2py. And the hard one, of course, is the z-axis. I'll try and draw that in red. The z-axis is coming straight out of the page at you and going straight back into the page. And the way that I'm going to draw that is I'm going to draw it coming out to the side like this and getting wider. And this is just the axes, by the way. And then I will draw a balloon. And that balloon, the line gets thicker out there. And I'll do an extreme zoom for you. So the line is here for the top of the z-axis, and then the balloon gets a little thicker near the top, and that's what's called forced perspective. When things get closer to you, they look bigger. And then when things get farther from you, well, they're very tough to draw, but when we draw them, we will draw them, and let me zoom out so I can draw this. We will draw them as dashed lines, as if they're harder to see or semi-visible. And so there will be a dashed balloon down there as well. And I apologize, I know this is tough to see. The third dimension, when you've got other overlapping dimensions, is always tough to draw. But it is something that in chemistry we will need to get used to, because the most important aspects of many chemical properties are related to shape. And that's where we're going, is how to do shapes of molecules. And we will use this forced sense of perspective with things that get closer to you being larger throughout the rest of the course. Anyway, that's a little bit of how you do it. And I guess I should label this red one as 2pz. So I label all my axes. But now we know the shapes of S's and P's, p orbitals, and we know how to configure them around the nucleus. If this question were about 3s and 3p's, 3p orbitals have the same designations, they're just larger. And let me zoom back out. So 3p orbitals for 3px would be balloons or half dumbbells that go all the way out to the edge of 3s. Because the idea is that when you have a 3s sublevel, that 3p fits inside it. And in fact, 3d fits inside 3s as well. Like 3s defines the largest shape for the n equals 3 principal energy level. Anyway, so I think this actually is the one question that is exactly like it is in the homework. And again, so these are the answers to this one question. And I will ask you, do you have any questions about it?